1, metabolism and energy.
Wait, did you do 1 for 1 yesterday?
No.
Oh, I thought you said 2. Oh my god. I'm sorry.
You're good.
The first number is the number of food.
Okay, she knows that. She got confused. Settle down, Toby. I think you're going to be all right. I'll remind you. Oh, can you go shut the heat off? That's great. Oh, but it looks like we're getting results. That's great. Hey, so what can we conclude about glucose and the particular semi-permeable membrane we made? Went through, because was there any glucose in the surrounding solution to begin with? No, it stays on to tell you that the top's hot. Did it click? Like, did it go to the left and kind of see? If you want to be sure, go to the other side and just unplug it. If you go to the other side of the bench and just unplug it, then we'll know it's off. That's great. Now, that's interesting. Sugar moved out of the cell, but what didn't move out of the cell? How do we know it didn't move out of the cell? Very good. Very good. And again, that's not a perfect one-to-one comparison with a cell membrane, but in this case, why do we think glucose went through but starch didn't? After all, starch is just glucose is put together. Too big. That's right. It's simply bigger than the size of the pores. All right. Anyway, here's what we're going to talk about. Energy can be defined in a few different ways, but the working definition we're going to work with here is energy is the ability to do work. Now, I want to be clear, this is not the only definition of energy, but it's going to be the one that we use here, this sort of thermodynamic explanation of energy. We're going to think of energy as the ability to do work. We could define work in physics. Anyone taking physics? What's work?
I should know this. Toby? That was like an entire summer ago.
Movement of force across a distance is classical physics definition, right? Force applied across a distance. But anyway, work can exist in kind of many different forms, and so can energy. What are some of the forms energy can exist in? Very good. Heat is a big one. Exists in many different heat. Exists in many different forms. And one we got was heat. Yeah, I like that. What else? We called it, does anyone know what we call heat energy? Thermal energy. Good. Yep, exactly. What else? Sorry? Sure. Yeah, absolutely. How do I want to write that? I'm just going to call that chemical energy, as it kind of falls into that category, but absolutely. That would include activation energy. What else? Come on now. Little kids got lots of energy. How do you know? You know because food. Got to be honest, that sentence doesn't make any sense to me. They run, they move around. What do we call that kind of energy? Kinetic energy. Good. Kinetic energy refers to movement, right? Good. What else? Potential energy. I love that. What else? It's actually a form of kinetic energy, but we think of it as its own thing. Sound, right? EM radiation. What's EM radiation? Yeah, such as? Yeah. Right, from radio waves to microwaves to the visible spectrum, right? To what comes after the visible spectrum? Ultraviolet after that. X-rays after that. Dr. Bruce Banner blasted by. Nobody? There you go, gamma rays. Dr. Bruce Banner blasted by gamma rays. Nobody knows the theme songs. Do you know the Captain America one about his mighty shield? You guys need to watch like 70s superhero cartoons. You probably don't even know the superhero song, the Super Friends song. We are the super. Anyway, do you guys know the classic Spider-Man? Okay, that's good. That's the big one, I guess. Is he strong? Listen, bud. He's got radioactive blood. Like, these are good lyrics. That's what I'm saying. Anyway, gamma rays. What else? gravitational. Right? Right? And weird as it may be, huh? How do we know that one? Somewhat famous. How do we know this? Why is mass a form of energy? What's the relationship between energy and mass? I think you do. Yeah, very good, right? So there you go. So, energy can come in lots of different forms. It's weird to think of the fact that your mass is just a form of energy, but your mass is just a form of energy, and it can be converted to other forms of energy. So what happens in nuclear reaction, right, is that you break apart a nucleus, you put together a nucleus, but in the process, a little bit of mass gets lost and gets turned into energy. And it turns out a little bit of mass actually produces a monstrous amount of energy because, as it turns out, this number, pretty big. What's the speed of light in SI units? 3.0 times 10 to the 8 meters per second squared. You don't have to write that, right? And then you square that number. Turns out a little bit of mass, because you're multiplying it by an enormous number squared, gives you an enormous amount of energy. That's how nuclear reactions work, because mass is just a form of energy. And if you can destroy, if you can annihilate even just a tiny little bit of it, it releases staggering amounts of energy. Yeah. Potential energy is the fact that, right now, this is full of all the energy it took to lift it up to a height. Now that's interesting because I actually didn't lift it to that height. I actually put it down to that height. But at some point, it got lifted to this height, and I lowered it here, and it still has all the energy that was put into it by whoever lifted it up in the first place. Maybe it was me, maybe it was someone else, right? And if I want to release that energy and have it stop being potential energy and actually turn it into kinetic energy, do that, right? And that potential energy became kinetic energy. That energy can never be destroyed. What happened when it stopped being kinetic energy? Still got some potential energy, but no. Sound. And interesting as it may be to think, that sound is currently spreading out throughout the whole universe. Now, because of the cubic nature of it, the fact that it's expanding over a volume, right? I guess it would be a surface area, so it would be a square. So with every meter it goes out, it gets less intense by the square of that distance, right? So it doesn't take long for that sound to get really quiet, but it's still moving. It's still going with that. That energy doesn't get destroyed. It has to go somewhere. Some of it got absorbed like little hairs in your ears, and they turned that into an electrical signal and a chemical signal that went to your brain. Does that make sense? But all that energy is doing something. You can't destroy it. You can convert it from one thing to another. So.
We'd like to make it into mouse.
Oh, sure. Yeah, have at it.
We're having a movie night tomorrow from 7 p.m. to 9 p.m. right outside the classroom. You can bring your own blankets, bring your own snacks, bring your friends. But we are having snacks being sold, so bring money for that as well. Support us selling snacks.
But you can also bring your own. But yeah.
And we will be playing Jumanji 3. And in the event,
Smash hit Jumanji 3.
And if there's any rain or
Who picked Jumanji 3? That is a very specific choice. Sorry? We're going to watch Rocky 6. Anyway, I love it. Is Jumanji 3 good? I have not seen Jumanji 3. Oh, excellent. Sorry? Well, now you know. You got to come see it. Anyway, these movie nights have been really fun. Actually, did you come last year?
Yes.
Yeah, it was a really good time. You should come. You should bring a friend. You can make a lifelong friend, coming to movie night. You might, who knows?
All right, Owen's trying to escape, guys.
You could find the love of your life. You never know. You could sit down with your blanket and your popcorn just thinking you were going to watch smash hit Jumanji 3, and you could stumble upon the person who becomes your forever friend. Right? Just saying. But you'll miss that opportunity completely if you skip it. Yeah, go.
In the event of any rain, it will be hosted in the cafeteria instead of outside.
Yeah.
Probably not.
That's a good question. I feel like you want
Cheese is
something.
Lysol.
I feel like if they have big alcohol wipes, that's the best thing.
Okay.
I feel like that Lysol. I'll say this: I've used alcohol wipes, and mine have been fairly undamaged going forward. I wonder if there's even just a product like computer wipes.
There is. I googled it.
Yeah, I'll just buy that.
Okay.
Yeah, whatever that is, seems trustworthy. Yeah. Yeah. Well, in part, I mean, sound energy is just a form of kinetic energy. It's just all sound is the particles in the air moving. So, this speaker moves back and forth. When the speaker moves forward, it pushes air forward. And when it moves back, it pulls a little air back. And it causes a wave in the air, and that spreads out. So that just keeps moving. And it just keeps, that particle bumps into that particle, which bumps into that particle and spreads out. Yeah. And the fact that it just keeps spreading out contributes to the eventual heat death of the universe, right? The idea that all the energy in the universe will eventually disperse so that's so far away from every other particle in the universe that they can't interact with each other in a meaningful way. Then we'll just live in we'll be long dead. But then the universe itself will just be, a big mass of energylessness. Anyway, let's get to the laws of thermodynamics. How many of you have taken physics? Okay, a little bit of help there. This should help you if you have, but you don't need to have. You'll be successful either way. Let's break this word down. Do you guys find it helpful when I break words down? Yeah. Okay, it doesn't just seem like a waste of time. I've always been of the opinion that it really does help understand if you just kind of take a minute to figure out what a word comes from. What does thermo mean? Heat. And in this case, that's being used as a stand-in for any energy. So really, this would better be called energy dynamics, because even though we call it thermodynamics, really that's being used as a stand-in for any sort of energy. And dynamics means if something is dynamic, like my lessons. So like it means boring and confusing. It means miserable. No, it means moving or changing. Dynamics means anything where Khan Academy does a better job of it. Anyway, so we're talking about the laws of how it is that heat moves or change, or energy moves or change. Does that make sense? And classically speaking, we have two laws of thermodynamics that we're going to work with. The first law is this. Energy can't be created or destroyed, but it can be transferred from one object to another or transformed from one type to another. By the way, this is a pretty big statement. Basically, it says that all the energy that exists in the universe has always existed in the universe and will always exist in the universe as long as there's been a universe. Does that make sense? You don't get any more of it, and you can't get rid of any of it. There's a static amount of energy, which is interesting. What can it be? It can be transferred. And it can be transformed. And let's break those key ideas down. Transferred means from one object to another. And transformed would be from one form to another. And this model of thinking about energy is sort of the foundation of all of physics and chemistry. Why did that happen? What, now we're just putting arrowheads on these things? Am I missing something? Whatever, it's got an arrowhead. I'm not fighting with it. Does anyone know the second law of thermodynamics? We've talked about. No arrowhead that time, but it was at a weird angle. Okay, there we go. Struggling with the auto ruler. It is the tendency of the universe Does anyone know the word we use to describe that tendency? Yeah. Close. The other one. Other one. Entropy. Yeah. You're close. You got it. You're good. So we call this entropy. So entropy is a measurement by one explanation, by one definition. I have a little video on entropy we're going to watch tomorrow, which sort of expresses it in a few different ways of thinking about it. But one way to think about entropy is it is simply the movement to disorder. Does that make sense? It's the movement. And what does disorder mean? Because that's a bit of a weird statement, but it's basically the idea that energy spreads out. And that we see that in the form of diffusion and osmosis, right? Where energy in the form of mass will spread out, right? We saw that here, where if you put a lot of iodine particles in one place and none in another place, then they try to get there, right? If you put a lot of glucose in one place, it's going to try to get to the other. Did we see mass movement? Cell shrink or grow, as a rule, right? They got more mass in them. That makes sense because we had a relatively low concentration of stuff outside the cell, right? We had a high concentration of stuff inside the cell, so that stuff inside the cell wants to spread out, and water moving into the cell facilitates that, right? If we had loaded the surroundings with salt, or salt would have just been able to move through. If we loaded the outside with starch, like if we'd done a 1% starch solution in the cell, and then like a 15% starch solution outside the cell, which you'd never get a 15% starch solution to dissolve, but you know, good. You'd have seen water just flow out like crazy. The cell would shrivel right up. So this is called entropy. So this gives us a question that we're going to try to think about as we go. How does life happen in an entropic universe? What do I mean by that question? Yeah, Toby.
Like, life is complex and needs a lot of energy to be built and whatnot. So if like the universe wants to be less organized, how did it build such complex things?
That's right. Living systems are complex. We could say ordered. And they require accumulated energy, right? Okay, so the question then is, does this disobey the second law? And we're not going to get too much into it, except to say you may well actually be your individual life, if you think about it. You destroy a lot more than you created. Stop and think about that. You weigh, anywhere between people in this room, probably 100 pounds and let's say, technically speaking, about 260 pounds. That's probably the range we have here, right? And that will be, you'll have brought that much material together and you will, fighting entropy, keep it there the whole time. Mind you, entropy is fighting you back all the time. If you don't drink water, what happens to you? You die because your water leaves your body, right? If you don't get new energy, what happens to you? You die because the energy leaves your body, right? Everything you do, what happens to your skin cells constantly. So you're fighting entropy your whole life, but basically you're maintaining this, anywhere from 100 to 262.25 pounds of mass at all times, right? How much much mass of the universe around you does it take for you to do that? Well, just back of the napkin. How many pounds of food do you think you eat a year? Let's say, hypothetically, you live on a steady diet of quarter pounders with cheese, one a day. Which I think, could you survive on that? I mean, not well, but you probably could. Every 4 days, that's a pound, right? That means every year, you're eating roughly your body weight in, just those hamburgers to survive. You know what I mean? So, like, just to keep you alive for 1 year is certainly more than your body weight just in food. And think of all the water, all the air you have to bring in. And every time you bring nutrients in, you're destroying something else that was ordered. Does that make sense? And you're breathing it out. And a good amount of what you breathe out makes its way into the universe. So even though on a small scale, your life decreases entropy, right? It makes more orderliness. The universe is actually sneakily using you to destroy all kinds of other stuff and increase entropy. Does that make sense? On the net. And remember also that your life is a flash in the pan on the life scale of the universe. It seems like a long time to you because it's all you know. But by universe standards, of course, the universe is 8.5 billion years old, right? And you are 16, 17, 19. Small little fraction of that. So you're a little blip of increased organization. And then, of course, eventually you will get disorganized again. And one thing I've learned about myself is you get organized and then you get disorganized again. Does that make sense? So it doesn't break the second law because life isn't creating order in the grand scheme of things. No matter what we do, we know that we're going to lose the fight with entropy, both on individual scale, right? Like part of a life cycle is you're born and you grow, but then also you decline, you die, right? That is just part of the cycle of every living thing on Earth. But also, more generally speaking, no matter how well we do, like our stars can expand to a red giant and engulf this planet in 4.5 billion years, right? Like that's just how it's going to go, and entropy will increase, And a star will collapse on itself, explode, and then entropy will really increase, right? Yeah. Disorganized means spread out, but it also means small. It also means existing in low energy states, which means if I let go of this, it's not going to stay up here because it's way more organized for it to somehow float in the air than for it to just drop and hit the ground, because that's a low energy state. So entropy really means that energy gets spread out, which includes mass. Mass will spread out, but also means energy. It takes a lot of energy held in this to keep it up here, whereas if it falls to the ground, hits the ground, and becomes a sound wave that spreads out through our entire planet, that's spreading that energy out. So that's the high entropy state. This is the low entropy state. In other words, that's the disorganized state with it on the ground, and this is the organized state with it up here. So it's not just particles that spread out, it's energy that spreads out. But one version of that is particles spreading out, yes. Did that answer your question? In other words, there's probably not enough gravitational potential energy to cause this to shatter into pieces and float all around when I drop it. So the mass itself isn't going to spread out, but the gravitational potential energy in it will, as it gets turned into some sound and some thermal energy and other things like that, and dissipates. Did that answer your question? Did it answer your question in a way that felt satisfying or helpful? Okay. Sure, I'll take it. Because this concept's weird, right? It's a weird concept. It's a little weird? Yeah. So what I'd say then is entropy applies to a total closed system. Overall, it always increases. But there will be local variations. And what I just mean by a local variation is there'll be places where things get more organized and entropy increases, or decreases rather. Okay, we can make it. All right. So, how do we locally break entropy? Well, we build things. How do we locally increase entropy and go with it? We break stuff. We destroy things. You build a pyramid, you are fighting entropy, right? You are carrying stones, and like you think of the incredible manpower who built those thousands of years ago. You know, like crazy things. You know, we're closer to the last pharaoh than the last pharaoh was to the building of the pyramids in terms of time. I believe we are. Yeah. Think about that. They're old. Things are old. So, yeah. So, like, just think about that. But the crazy thing is, all of those workers who put the energy into that stone, those workers are long dead. Possibly buried with the pharaoh, this was I think the workers have probably lost them, but their energy is still in there. The potential energy of each of those stones, that all that work that went into putting it up there, it's in there. And one day when the thing collapses, if it ever collapses for some reason or other, that energy will come back out. You know? Yeah.
You actually believe that people build pyramids?
Yes, of course. Like, oh my God. Because of course they do, because what did if people didn't? Dinosaurs, interesting. Okay. Aliens? Okay. So you don't think people could build a pyramid, but you think aliens could.
Yeah.
And what you think is they had nothing better to do than to come here and build a pyramid out of stones. So they have the advanced enough technology to build like interstellar travel, but they got here and they're like, all right, guys, now we're going to build shit with stones. This is what you think. See, that's not what I think, because I don't think that makes any sense. Whereas I think it makes perfect sense to say to a bunch of people who have nothing to build things but stone that they would build a big building with stones. You see what I mean? There's a bunch of competing theories. Yeah, there's a bunch of competing theories. Some believe that the actual structure itself, there's some evidence that there were internal rampways, so that like as they're engineering the building itself, the actual stones they're using to construct it are actually forming a ramp that they're then going up. There's other evidence that they think there were external ramps. One of the really neat things you can study is there's a few pyramids that started out as step pyramids, and then somebody else came along later after the fact and built around them and built them into the ones we think of. Have you ever heard of the bent pyramid? Which is a really interesting example. Our best evidence for that is they were trying to build the steepest pyramid they'd ever built. And they got to a certain height and realized this thing wasn't going to be stable. So it goes up like this and then changes angle and goes like that. In the middle, it looks kind of derpy. And you think something that probably took 60 years and hundreds of thousands of people working at slavish, long hours and hard work to end up with something that looks kind of stupid and derpy at the end is sort of embarrassing. But yeah, so we actually have a lot of evidence of how they were built because you can actually see the evolution of how they were built over time, which is another thing where you're like, it's probably unlikely that aliens came here in those spaceships made of metal and with interplanetary stuff and started out by building really basic crude pyramids and then over several hundred years got them slightly more complicated. You know what I mean? I'm not trying to be dismissive, but I know I am trying to be dismissive. I'm not trying to be rude, but yeah, no, aliens didn't build the pyramids. There was a famous book, by the way, that that I read when I was young called Chariot of the Gods by a guy named Eric von Daniken, which is all about that's what set on fire the idea that the pyramids were built by aliens, and he makes all these allusions to if you read the story of Daniel, it talks about chariots of fire and wheels of fire, and obviously that's talking about spaceships and stuff like that, but it's pretty heavily debunked and obviously not true. Egyptology is a little bit of passion of mine, so we can't talk about it now, but if you're curious, I'd love to chat because it's it's a thing I'm really interested in, actually. Anyway, back to the topic at hand. Sorry? Oh, yeah, no, this lives on. I'm so proud. Making Mama proud since 1983. Anyway, let's get to it. Yeah, we fight against entropy by building things, and we work with entropy when we destroy things. And we do that at a macroscopic scale. We do that as people, but our cells do that too, right? They create and they destroy. And they create and things destroy on their own. They degrade on their own. And we call this metabolism. Specifically, we're going to talk about anabolism and catabolism. Anabolism and catabolism. And we'll just say this. In living systems, large molecules are frequently put together and taken apart. Yeah.
The prefixes in animalism and metabolism, does that have any relation to anion and cation?
Yes. And we'll talk about that. I've always struggled with these prefixes, which is why I'm not highlighting them and explaining what they mean right now, because it has always struck me that they seem to come up opposite to how you expect them sometimes. One day is, because it's also where we get anode and cathode, obviously, and yeah, we'll talk. I've always struggled to come up with a really good way to explain those prefixes in a way that will always make it clear when they're being used in which way. But anabolism is the formation of complex molecules from simple ones. Anabolism is the formation of complex molecules from simple ones. So we learned about this last unit, right? In our reactions, like a condensation reaction, right? The formation of complex molecules from simple ones. Got it. So, okay. Yeah, give me 1 second. I'm gonna get the next sentence up here, then I'll answer your question. Okay, I don't want to run out of time. So we'll draw a quick picture, and then you guys can have time to draw it. So the basic idea then would be that we have a bunch of simple molecules here. Oh, look at them all. There they are. And what we're going to do is maybe we'll start to form dimers. So maybe these will pair off. That would be a form of anabolism, right? Taking what used to be individual molecules and pairing them off. And maybe from that, we can end up making a polymer, right? Like just a big, long, continuous chain like this. Now, what has to happen at each step along the way to make that happen? If you want to stick things together, you've got to insert energy. Has to go in, right? It just has to. It takes energy to put things together, which means that what we have here is a low energy state, which is also, as it happens, a high entropy state. So in this situation, energy is low, but entropy is high. What about over here? Now this molecule is a high energy state, but it is a low entropy state, right? In other words, entropy, this is doing well. These things are all able to spread out. They can move freely. Here, the entropy is low. They're stuck together. They don't have that degree of freedom. They can't move freely. On the other hand, here, these don't yet have a bunch of energy put in them. To lower the entropy of the system, we had to put in a bunch of energy. Does that make sense? Cool. Copy that down. Yeah, let's take a look. Maybe you could relate to that. Specifically, I just want the idea. Just say you're building a protein. I want that protein to be transmembrane. So you need to know what that means. And you can probably figure it out. Trans means membrane is. So you can even draw a membrane, what it's actually made of, and draw like a protein that is trans to that membrane. And then we're saying here that there's going to be a section of that protein that's embedded inside the cell's membrane. All right, so the portion of that protein that has to deal with being inside the membrane, what would it have to be made of? Versus the portion of it that is out and is exposed to the water inside the cell and the outside the cell, the top surface and the bottom surface of the membrane. Which of these would be appropriate choices for that? And it's thinky. I want to see your thinking. All right. So And maybe it would be helpful here. Low entropy is another way of saying it's more organized, right? It's weird because entropy is this almost like we think of it in negative terms, right? It's sort of the high entropy, on the other hand, is less organized. So that is what an anabolic reaction looks like. And we could refer to this as an anabolic pathway. Which is just a way of saying that it's an anabolic reaction that happens in stages. Does that make sense? We don't just go from here to there, but rather we make little steps towards anabolism. So it's an anabolic reaction that happens as a series of smaller ones. And if you think about it, that makes sense. What would take, in either case, when we go from here to here, we know how we're going to have to change entropy by a certain amount, and we're going to have to put a certain amount of energy in. But can you imagine how challenging it would be? Say you wanted to build a molecule that was, I don't know, not 4 monomers long, but 100,000 monomers long. Are you really going to do that in one step? Have all those monomers bump into each other and just come together in the right shape? Could you imagine how hard that would be to build? Imagine a factory where they want to build a truck, but they want to do it by literally rolling in a sheet of sheet metal and having one machine just go whoop, and then a truck comes out at the other end. Is that very likely? Is that how we build factories? Of course not, right? You do it in multiple stages and multiple steps. But why? Why not just do it in one step? Wouldn't that be more convenient? Yeah, it's just that you have to put energy in to fight entropy, and the amount of energy that would have to be put in to make a big change in entropy like that simply isn't feasible. It's just not possible. But if you break it into small steps, now you're only overcoming a little bit of entropy at a time, and you can deal with that. And we're going to see the equation of how that works in a minute, well, in about 4 minutes. So that's anabolism, and that's an anabolic pathway. Okay. What is the other one? Metabolism. You know what? Should we? Yeah, we should mention that actually. We're going to put a star here and say reducing entropy always requires the input of energy. The universe doesn't get organized for free. We think that life first started, the best estimates we have right now is that they did the earliest molecules of life, and we think the likely contenders for that are phospholipids forming a membrane and actually RNA forming. Because RNA, we haven't talked about this yet, is interesting because it can serve as both a genetic material, but you can also build enzymes, simple enzymes out of RNA. RNA can it has sort of protein-ish, protein-like properties. Because it's only single-stranded, double-stranded DNA folds in that very predictable way. It doesn't matter what the nitrogenous base is because the nitrogenous bases are held on the inside. RNA, because it's single-stranded, the nitrogenous bases are exposed, and so they can actually fold into different shapes. And so RNA can serve both as a genetic material and as a simple enzyme, though it's not nearly as effective as proteins at being enzymes. So our best guess is those did form spontaneously, but our science shows that we think it was likely in a hot spring, where there's lots of what being put in? Energy, or in a geothermal geyser under the ocean, where what's being put in? Lots of energy, or maybe a lightning strike, where again, what's coming in? A lot of energy. What we know is that if you're going to reduce entropy, if you're going to make a complicated thing, you're going to have to put in energy. This is like almost philosophy in a way. Do you know what I mean? Like it's pretty heady stuff. Does that feel reasonably okay? Yeah? It's a bit weird, right? A little bit weird to think about. But what's the opposite of anabolism? We said catabolism. Catabolism? I've always said catabolism. Sorry? Not cannibalism, different thing. Though also an example of catabolism, interestingly, I suppose, because you would indeed be breaking down molecules. But, frowned upon in most circles. Okay, so this is simply the opposite. It's the breaking down of complex molecules into simple ones. So we could start with that polymer that we had, that complex molecule, in this case, kind of a chain. And it actually is much easier to break something down. You can break something down in one step. You burn it, it breaks down pretty effectively. But still, catabolic pathways will tend to do this in a step-by-step fashion. Unlike anabolism, you don't have to go step by step. But the advantage of going step by step might be what? What do you think? We could probably just, throw some oxygen at this, throw some heat, burn it, and boom, it'll just break apart. Yeah. What a great answer. You can retain the pieces you want. Whether that means not breaking it, maybe you don't want to break it down to its smallest possible pieces. Maybe you want to use it as still somewhat constructed, or maybe just retaining more of the energy. You can capture the energy more carefully. Now, at each stage here, if every step of building a molecule involves putting energy in, then if we go the other way, what must happen? Energy must come out. All right, that's the first law of thermodynamics, right? Energy can't be created or destroyed. It just moves from one place to another and converts. So if going one way involves energy coming in, then going the other way is going to involve energy release. Yeah, you need to put some energy in to start. But that's true, right? Like if you think about your furnace, it needs a pilot light, right? If you have a gas furnace, it needs a pilot light. You got to give it a little bit of energy to get started. But on the whole, does your furnace take energy in or put it out? Puts it out, right? Yeah, you need that little bit of energy to start it. Does anyone remember what we call that kind of energy? Activation energy. And that's to kind of quote unquote get the ball rolling, right? In other words, all that means is that the energy that is where it is right now for some reason is in a stable space, right? Even though this has all that gravitational potential energy, gravity's trying to pull it down, this is holding it up and it's in an equilibrium state where it's, even though it's not at its lowest possible state, it's stable, right? But a little bit of activation energy, I don't have to push this all the way to the ground, right? I just have to push it so that's no longer in a stable spot, and then its energy will come out all on its own. And it provided a lot more energy than I did. And that might not be that obvious with that being just a little thing. I just gave it a little tug. But if you, have a precariously placed giant boulder at the top of a cliff and you just give it a little push, it's going to give away a lot more energy than you put into it, right? Your little push is the activation energy. The force of gravity taking all that gravitational potential energy and turning it into kinetic energy and eventually turning it into crushing energy or shattering energy is the big source of energy. And that was already inside of it, just waiting to be released. Did that answer your question in a useful way? Look at that. Now, in this case, we are starting with a high energy, low entropy setup. And we are ending up with a low energy, high entropy situation. And catabolism must, by definition, result in the release of energy. Simply must. So catabolism always releases energy. And again, that doesn't mean it doesn't require energy to start. Every reaction requires some energy to start. Otherwise, it would have started a long time ago, right? But on the net, if you add up what's released versus what was put in, you're going to get a net release of energy with a catabolic pathway. And then, of course, you're not used to the terms catabolism and anabolism. What are you used to? Metabolism. But meta just means across the whole spectrum. So metabolism is just the system of catabolic and anabolic pathways in an organism, right? An organism's collection of anabolic and catabolic pathways is referred to as its metabolism. So this is the collection of anabolic and catabolic pathways so I don't say in an organism. I regret this ordering. But whatever, we'll just say an organism has, I guess. That's super clumsy. Take that one back to the drawing board. You know, it was a good sentence, the one I wrote here that I was going to write. But that's okay. I got ahead of myself. Sure, you gotta give me a second. Okay, I don't want to run out of time here. All right, so really quickly, we're not going to, listen, you could spend a whole career studying this. We're not going to do that. But we are going to quickly, very quickly, present you with a formula that will refer back to at various points. You're not actually, you're not actually going to do a lot of math in this biology class. So don't worry about that. But I do want to, I want to start this today. And then, in fact, we're going to present the formula, we're going to mention it, and then we're going to go from there. Okay, I'd like you to write this down. Delta G equals delta H minus T delta S. Huh? Delta G refers to a change, all right, in free energy. What about this makes it clear that we're talking about a change? Sorry? Yeah, and absolutely the delta, right? The triangle. That symbol in science is used to mean change. And basically, we want to know how much free energy is available. In other words, how much energy can actually be used to do work. And we're going to talk about this tomorrow. But for any reaction, we want to measure how much energy does it actually free up. And of course, what kind of reaction actually frees up energy? Anabolic or catabolic? Catabolic. So catabolic reactions will actually free up energy. So they're going to increase free energy. On the other hand, anabolic reactions will actually decrease free energy. Does that make sense? If you've taken chemistry, you'll be familiar with this term, delta H. Do we remember what that is? Kiki, go.
I'm sorry.
No, you said it like 5 minutes ago. You know this one. It's the other energy term. Entropy and? Very good. This is enthalpy. Which is the energy gained or lost by the chemicals themselves. Now, in chemistry class, we actually just talked about delta H. Because in chemistry, we kind of assume that energy released is energy released and who cares. But biological systems know that when energy gets released, you don't get to keep all of it. This is the part we get to keep and that the cell can use for something. It can do work with. It gets this, but then it also loses some else. What does it lose? Well, it loses some to the other thing we deal with in thermodynamics. We deal with energy and we deal with, so enthalpy and entropy. Does that make sense? What's the T? Temperature. Why does temperature matter for entropy? Can, but the temperature something happens at has a lot to do with how entropy works. And you actually know this intuitively. If you want something to spread out fast, you want it to be hot or cold. Yeah, if we put dye in hot water and dye in cold water, which one's going to spread out faster?
Individually? Or how do you get them
Individually.
I thought maybe you wrote like a script or something.
There is one. Cleves wrote a macro.
Yeah.
And I have it somewhere and I can have to find it. Yeah, so temperature is going to affect entropy. In high temperature systems, you lose more to entropy. In a high temperature system, things will spread out more. Does that make sense? In a low temperature system, you can actually contain the effects of entropy. So this is the formula we're going to talk about when we get going tomorrow. Again, we're not going to use it as a math formula all that often. Maybe once or twice as a little example. But we are going to use it as a guiding principle. Does that make sense? The question, how is life possible? The answer is, it's always just a trade-off. You can get energy to do work by releasing energy from a reaction, but you just know that it's always going to be in a counterbalance with entropy. Because what do we notice about the signs of these two things? This one is, and this one is, which means in any reaction you're doing, if this one's going up, this one presumably is going down. If this one's going down, this one presumably is going up. And that's what we saw in our anabolic setup, right? When we build things up, we have to put energy into it, right? In other words, as we make entropy go down, we make the system less entropic, more organized. The energy has to go up, and vice versa. Does that make sense? So I don't want you to think about this as a math equation. It is. And if you get into like biophysical chemistry, oh boy, you'll use a lot of this. It's not that complicated. But right now I want you to think about it as a principle, which is it mathematically explains that you can trade one for the other. You can trade energy into enthalpy, or energy into entropy, or vice versa. So that's where we're going to leave it for today. We've got a couple of minutes left. Why don't we go do a quick cleanup back there? You can take your